Let's jump right into the equations now that we have a little background. We'll look at atmospheric modes in a constant basic state. Stationary state is of course a constant basic state. Let's start with that. You remember the equations we wrote for the ray path. So once you have a wave number k and the background state, basic state, you have this ray path, and if the basic state is motionless, then obviously wave numbers in the vertical, zonal and meridional directions do not change in time. That's what this equation says, which we got during the wave kinematics. In chapter 5 we decided Laplace's spherical shallow fluid, where we said there is a bottom topography, there is the average depth, equivalent depth in the case of stratified fluid. You have the slope of the surface that supports the mean state in geostrophic balance. We will see what happens when you have easterly basic state and westerly basic state as well, and see what contradictions arrive if you try to impose certain things like the slope required and what happens to the depth of the fluid as you go beyond a certain latitude. So the total depth is written this way of the water column we are dealing with. Obviously we'll also look at assumption called rigid lid, which also affects the solutions of the wave modes that we are looking for. So here the fluid depth as a function of longitude, latitude and time is this mean depth with this thin black line plus the slope for the meridional slope. We are thinking of kind of the zonal mean meridional section here. So this is the range we are looking at, A to B, C to D. So this latitudinal section, assume that we have removed the longitudes by averaging, but we will soon come back to longitudinal solutions on the equator as well, obviously. Then you have the sea surface height deviations or the geopotential in the atmosphere, and you have the bottom topography. Okay. How did we derive the equations? If you remember, we started with the shallow water system, where you had the acceleration, the full equation with the acceleration term, Coriolis term, and the vertical terms with no forcing for the zonal and meridional directions, and for the vertical direction with the mass source. We integrated in the vertical. We took this out with some assumptions of hydrostatic balance and so on. So we ended up by linearizing the system with these kinds of linearization. U is u bar y, again just the meridional function of the zonal flow with perturbation velocities. Same for the meridional, except that the basic state of the meridional velocity is 0, so the perturbation is the same as the basic state. Well, that's not the best way to say it. And h is h bar plus hs plus h prime xyt, so we are making small perturbations to the surface with the basic assumptions we always use, that the perturbation velocities are much smaller than the basic state, and perturbations to the sea surface height are much smaller than the depth of the fluid that we are looking at. So we can then impose conditions like u prime and u prime u are much greater than the perturbation multiplications, and average depth is much greater than the slope that we are going to impose for certain basic states and meridional shear. So we ended up with these equations in the for the momentum and vertical, and I'm not going to dwell on this, but you remember things like how if h bar is very large, then the flow becomes non-divergent, because these terms become much smaller than these terms. So then du prime dx plus dv prime dy has to be very close to 0 or 10 to 0 if in a deep fluid. So we wrote out of that the equatorial wave equations for the x, y, and vertical direction again. Okay. We linearized, then we developed Eigen Solutions of the type u prime, v prime, h prime, as where r is the real part of this solution, right? We have the meridional variations in the fluid depth as the waves propagate out in east-west and meridional directions. We will see how the meridional modes will be related to this fluid depth in the meridional direction. And we have, of course, the wave number and frequency terms. We derived these equations. We defined Doppler shifted frequency and the essentially vorticity terms, which we'll come back to later on when we look at ocean flows. So we have here the gravity wave speed and Doppler shifted frequency with the intrinsic frequency, zonal wave number, and the basic state. That gave us this equation, which is rather complicated to derive, so we looked at the details from Appendix D. So that's where we will return to here with Py and Qy having these complex forms with dependence on stationary flows. Jumping straight to where we wanted to start, in a basic state that is stationary, u bar is 0, so Py is 0, and Qy takes this form, which is obviously a dispersion equation, because you have a relation between frequency and wave number. So spatial and temporal scales are going to be coupled. Then you can write our equatorial wave equation as d squared v dy squared plus this term times v equals 0, which we know is the Schrödinger harmonic equation for a geophysical system. Non-dimensional form of this can be derived by using c over beta to the 1/2. Again, c is the gravity wave speed, and 1 over beta c to the 1/2. Then this equation can be written as d squared v dy squared plus this simplified looking thing where this can be written as a minus by squared, where of course a is these three terms and b is 1 in this case. We introduce this because later on we will need cases where b is not 1. Okay, so non-dimensionally a is this, b is 1. Dimensionally, using the non-dimensionalizing parameters, a is omega squared over c squared minus k over omega beta, and b is beta over c. So when we non-dimensionalize, b is 1, but in a dimensional form it's not 1. Okay, you begin to see the relations. I'll start this equation part here, and then we'll continue in the next podcast on what kind of solutions evolve out of this. Okay, it turns out that the basic state being stationary is a simple case, obviously not very realistic in the sense that neither the ocean nor the atmosphere in the tropics are really in a stationary state. So we will immediately add a basic state that is easterly or westerly, and then we'll complicate it by adding meridional shear as well. All of them are still simple in the compared to the real world, but these give us the full range of solutions of how the wave mean flow interactions happen.